All right, so yesterday we spent the class talking about position versus time graphs. Okay, so things we got to remember, okay, that will apply to all graphs will be some things we'll go over today again, which is, when we're being asked to calculate something, we want to look at what things are we working with, and that can help us to decide, what is the slope going to represent on this graph as opposed to memorizing it. Okay, what other kind of things can I calculate? If a question asks me to look for this, how am I going to do that? All right, those kind of things, we'll be reviewing those, and obviously under a new context of velocity versus time graphs. Okay, and then we'll look at solving some problems that are like what you're going to get on quizzes and tests, okay, to do with velocity versus time graphs, just like we did at the end of the day yesterday. All right, so velocity versus time graph shows how fast an object is going and in what direction at various points in time. All right, in the same way that yesterday a position versus time graph showed where an object was at various points in time. Okay. These two pictures here, I've got a position versus time graph and a velocity versus time graph. I think you would agree they look different. Okay? They're actually showing the same thing. Okay? Yesterday when we looked at position versus time graphs, we said if we had this kind of a pattern where we had the points going up like pretty much the same amount every time interval, that object was traveling at a constant velocity. Okay, constant speed would also be accurate, but okay. Is that what this velocity versus time graph is showing? Yeah, right? It's showing that the velocity is not changing. In other words, it is traveling at a constant velocity. Right? Now, if I had that shape on a position versus time graph, the object would be stopped. Okay? But in this case, again, looking at what is this graph showing? It's showing no change in speed this time, or sorry, velocity, versus on the other kind of graph it was showing no change in position. Right? So while the shapes are similar, they mean different things. Everyone kind of follow me on that? All right. How can I figure out what velocity the object is traveling at from the position versus time graph? Anybody remember from yesterday? Okay, this graph is showing me where the object is at various points in time. All right, I want to figure out how fast it's moving. So, what are the units for velocity? Oh, that's not good. We should really know that one. Units for velocity are meters per second. Okay, so if I've got meters here and seconds down here, if I find the slope of this line, will that make me divide meters by seconds? It will. All right, so the slope of this line then should give me the velocity of the object. All right, so I'm going to find 2 points on the line. I'm just going to use the beginning and the end because they're both at grid intersections. Okay, just it starts at 100 down here. All right, so we'll do our y2 minus y1. So y2 is 1400, okay, minus 100, okay, over 5 minus 0. Okay, so we got 1300 over 5, which is what, 265? Something like that. $260. All right. So we've got a velocity here of 260 meters per second, and that's forward. Is that what that graph is showing? Yeah, it is, right? Okay, every line on here is 50, so 150, 200, okay, 250, and then it's just slightly above that, so that's showing exactly the same thing. All right? Okay, what if the graph had this shape? Now what's going on that graph? Sure. Right, it's increasing its velocity. The velocity is now changing in a forward direction. Okay, the other word for changing velocity in a forward direction would be accelerate. Okay, that's an accelerating object. Okay, so this object's going faster and faster and faster. What's that going to look like on the position versus time graph? Okay, steeper in what shape? Is it actually going to be a line even? It's going to be a curve, right? Okay, because we said on this kind of graph, an accelerating object needs to cover more distance each consecutive second than it did the second before in order to indicate that it's moving faster and faster. All right, so that's those two shapes. They go together. All right. Now what's that graph showing? Right, it's decreasing its velocity. It's accelerating in a negative direction. Okay, if this continued, could it go down below 0? Yeah, it could. It would just begin to travel backwards. All right, so this could actually, if I continued to make this line go down below the x-axis, okay, that could represent an object that was initially thrown upwards in the air. Okay, because it would start out with a positive velocity, and its velocity would decrease, okay, as we follow the line. It gets slower and slower until it's instantaneously changing direction, right? And now it begins to actually move in the direction in which it's traveling. Okay, on a position versus time graph, we looked at that yesterday. Okay, that's when the graph had that shape, right, where it was going, slowing down. The curve was getting flatter, and then it actually started to move backwards the other way. All right, and then returned essentially to the same position. That would be where I threw it from, if I caught it and threw it from the same height. Right, so that would be that graph there. Right? So we can show the same thing on two different graphs. The thing we have to realize is they're going to look different, even though they're saying the same thing, because they're measuring it differently. Okay. So a plot of velocity versus time and distance versus time obviously look a little different. Okay. On a velocity versus time graph, okay, each point has the same vertical value because the velocity is constant. In other words, okay, on this graph here, okay, the flat line, we're traveling at a constant speed, okay, because everything has the same vertical value. In fact, I don't know why I underlined that. Forget that. I didn't underline that. It doesn't make any sense for me to underline that. Okay. So this is a velocity versus time graph, okay, of a runner in a race. Okay? When you start out a race, what do you have to do? You have to start moving forward, but you're also going to accelerate, right? You're going to speed up, right? Because you start a race from a standing start, right? And that's pretty much what this is showing. Here, the initial velocity is essentially 0, and then they accelerate, okay, quite rapidly. There's a little bit of a curve because the acceleration is not uniform, okay? But after that, it's pretty much a straight line showing a uniform acceleration. And then, what happens to them here in this part? Right. I mean, you kind of reach your top speed, and you can't accelerate anymore, right? And you can kind of see that in a runner. You can see, like, if you ever watch a race, for the first little while, everyone's kind of low, and they're kind of coming up, and they're getting faster and faster, and then they just kind of maintain that speed until they get to where? Right, to the finish line, and then they very rapidly do what? Yeah, slow down and come to a stop. All right, so that's what that would look like on a velocity versus time graph. Okay, if I want to calculate the slope of a line on a velocity versus time graph, I have to look at what is that going to tell me, right? Because obviously if we have a line, it's probably going to be valuable to calculate its slope. So if I do that, and I'm just going to erase all this and start it over again. All right, so if I start out with a velocity versus time graph, you might want to draw this. Okay, so let's say that I've got points that look like that, okay, and I draw my best fit line, okay, through those points. Okay, so now I've got my best fit line, and I want to calculate its slope. But I got to figure out what that's going to tell me. All right? So what I want to look at is, first off, this line tells me the speed is changing. Agreed? Right? And it's changing over the course of time. So if I do a slope calculation, let's say I'm going to use a point that's right here, and we'll say that that's even with 7, okay, and even with 8 down here. I know that's not quite, but okay. And we're going to use, let's say, this point right here. That's even with 1.5 and 2, we'll say. When I calculate the difference between y2 and y1, I've calculated the change in what? What's on the y-axis? Meters per second. So I'm finding the change in velocity. Okay, so y2 minus y1 equals the change in velocity. All right, and I'm dividing that by x2 minus x1, which is the change in what? Time. Okay, look on your formula sheet. Do you have a formula that looks like that? That is the delta V over delta T? Yeah, you do. What does it say it calculates? Nope. No, that's delta D. Oh, right here. Average acceleration. Okay, this is the formula for average acceleration on your formula sheet. It's about halfway down. Okay, halfway down. So the slope of this line is telling me acceleration. Okay, acceleration is the rate of change of speed or velocity. Okay, and its units are going to be what? The units for speed are meters per second. And I'm dividing that by time, whose units are seconds. Okay, now, seconds don't cancel here, right? Because if you remember how you do fractions, okay, meters per second divided by seconds, okay, means you got to reciprocate and multiply. Okay, so you're actually doing this. Meters per second times 1 over seconds. Well, okay, that gives me meters per second. What's seconds times seconds? Seconds squared. Okay, in other words, this is meters per second. How fast I'm changing my velocity. How many meters per second faster did I go each second? Okay, meters per second per second. All right, everybody follow me there? Okay, okay, where did I lose you? Okay, let me try it this way. Yesterday when we found the slope of the position versus time graph, we said that that told us how many meters I went every second, right? Because I divided meters by seconds. On this graph, I'm dividing meters per second by seconds. So it's telling me how many meters per second I went faster than I did the second before. Okay, so if I'm, let's say, falling, okay, on Earth, all things fall at the same rate. They accelerate down at 9.81 meters per second. So that means when I jump, if I just like fall off of a building, okay, then there's a big mat below me, okay, and I fall off of there, okay, and after the first second, okay, I'm going to be going quite a bit faster than I was initially. Every second I'm going to go 9.81 meters per second squared faster than the second before. Okay? Yeah. And that picks up in a hurry. Like after 2 seconds, basically you're falling faster than anyone could possibly run. All right? So falling for 2 seconds, you fall a long way. Right? Because after 2 seconds, you're moving at 19.62 meters per second. Okay? That's probably longer than this room is wide in 1 second. Okay? Like that's really fast, right? Like to give you an idea, Usain Bolt's top speed is around 17 meters per second. Okay? When he's at his absolute top speed. Now, can you imagine if he came to a sudden stop? Okay, like if someone played a joke on him and put a wall at the finish line. Okay, like he would be badly injured. Okay, coming to a stop from that speed would seriously injure you. Okay, so what we're saying here is how fast I change my speed is acceleration. Okay, everyone follow me on that? Does that make more sense? How quickly I change my speed, or how quickly I change my velocity, is my rate of acceleration. All right, so that's what the slope will get me. It is also possible to calculate how far the object travels from this kind of a graph. Okay, so let's have a look at that. Let's say I've got an easier graph. Let's say that my velocity versus time graph looks like this. So this object is traveling at a constant speed. Let's say that constant speed is 2 meters per second, right? And let's say it does that, let's say the time goes up to 4 seconds. How far is it going to go? If it goes at 2 meters per second for 4 seconds, 8 meters. It's going to go 8 meters. Okay, Taylor, how'd you do that? Multiply velocity by time. In her head, she did this. Okay, she manipulated v equals d over t. Okay, multiplied those two numbers, and she got the distance that was going to be traveled. All right, and that's exactly what you do need to do. Is that the same as calculating the area of this rectangle? She went height times base. Agreed? Base times height gives you the area of a rectangle, right? Because on this graph, when I multiply those two things together, I'm finding distance. Now, the other way you can figure that out, rather than memorizing it for this kind of graph, is once again to look at the units. If a question gives me this kind of graph and says, I want you to calculate distance, I need to go, all right, my units have to be meters. And the units I have on my graph are meters per second and seconds. So what do I have to do with meters per second and seconds in order to make the seconds go away? The answer is I have to multiply them. Okay, which is what we just did. We went v times t. Right? So there's a number of ways to look at it. You can look at formulas and integrate them with the graph, or you can look at units, okay, and figure out what mathematical operation you need to do. Okay? Either way will work, and either way will work for any kind of graph, right? Rather than memorizing what I can get and how I can get it from each kind of graph. Okay? So if I multiply these two things together, it's the same as saying that. Seconds cancels. I'm left with meters, right? And that's exactly what we did right here. Multiplied meters per second by seconds. All right. Similar situation. Now I want to calculate the distance traveled. Change what I do? In actual fact, it doesn't change it very much. Right? We just said that on this graph, we found this area by multiplying the average velocity by the time over which we traveled. Everyone okay with that? It's just that the velocity didn't change, so the average velocity just happened to be 2 and it didn't change. Down here, this object's not traveling at a constant speed. It goes from 0 to 5 meters per second in 4 seconds. What's its average speed then if it was starting at 0 and going to 5? Would its average speed be right in the middle? Okay? Because it's a straight line, I can say, you know what, the average speed of this thing is exactly half of this. Because I can say, half of the trip, it was going slower than that. And half of the trip, it was going faster. So the average is right in the middle. Now, that only works for this shape, okay? But it'll work. So I found the area of the rectangle up here, and it gave me the distance traveled. How do I find the area of a triangle? Base times height over 2. All right. So if I go the base, 4, times the height, 5, over 2, is that the same as saying 4 times 2.5? Is that what we said the average speed would be? Half of 5? Okay, see how this is working? Right? I'll get the distance traveled, okay, by doing that. All right. So on a velocity versus time graph, the vertical value of any point is the instantaneous velocity at that time, because it's a velocity versus time graph. I can read velocity right off of the graph. Okay? And the area under the line on a velocity time graph is equal to the displacement of the object from its original position. Okay. And the last thing, it's not written on here, okay, now we haven't talked about acceleration yet, so we're going to talk about next week. Okay, but because we're talking about graphs, we kind of introduce it here because it is something that we can calculate from this type of graph. Right, so believe it or not, there's actually more that you can get from a position versus time graph than you can from a velocity versus time graph. All you can calculate from this kind of graph is acceleration and displacement, and that's it. Okay? Those are the only two things you can calculate from a velocity versus time graph. Right? But from the position versus time graph, we could calculate displacement, we could calculate distance, we could calculate speed, we could calculate velocity. Right? There was way more things we could get from that graph. Okay? But we can't get acceleration from a position time graph. That's what makes velocity versus time graphs useful. Okay. Now we did that one yesterday and that one yesterday. All right, we'll try this one together here. So this is a velocity versus time graph. Okay? And it wants to know the acceleration between 12 and 14 seconds. Okay, so here's 12. Okay, there's where 12 seconds is, and here's where 14 seconds is. All right, so we do have a straight line, okay, an angled straight line. Can I get the acceleration from that line? What do I need to calculate about that line? Oh, we just wrote it down. I need to calculate its slope. Okay? Remember, acceleration is how quickly I change my speed. How quickly I change my speed is the change in speed, y2 minus y1, over the change in time. Okay? That would be x2 minus x1. Right? The slope of that line. Right? Remember, we just said a minute ago that y2 minus y1 over x2 minus x1 was really this, the change in speed, or change in velocity, sorry, over the change in time, and that's acceleration. Right? That's on your formula sheet. So you might want to write on your formula sheet, right next to that formula, okay, that's also the slope of a velocity time graph, just as a reminder. Okay? That's where, if you remember, one of the points at the beginning of this lesson yesterday was showing that the formulas on our formula sheet are derived from graphs. Again, there's another prime example. The formula for acceleration is derived from the slope of a velocity time graph. All right, so we want to calculate the acceleration between 12 and 14 seconds. So here's what we're going to do. We're going to plug in our numbers. All right, the velocity at time 12 seconds is 2 meters per second. Sorry, that's y1, so I don't want to use that yet. Okay, the velocity at time 14 seconds is -6. So I'm going to have -6 minus 2 over 14 minus 12. Right, so that's going to leave me with -8 over 2, which is -4. -4, and this was in meters per second, and this was in seconds, so my units will be meters per second, okay, which we often write as meters per second squared, right, just because it takes less time and it's quicker to say. Okay, everyone follow me there? Okay, all I did was find the slope of that line. We can all find the slope of a line, right? Okay, what we have to do now is remember when we need to do that. All right, total displacement over the whole trip. Okay, total displacement is going to be in meters. Agreed? All right, and we just said that if we calculate the area under the line, that would give us the distances. Agreed? Okay, so can I make a whole bunch of shapes here and calculate their areas? Okay, try that. I'm going to give you a few minutes before I do it up here. All right, I want you to calculate the total displacement over the whole, total distance traveled. No, displacement over the whole trip. Okay, by calculating the areas of all of those shapes. All right, now, give you a little hand with the shapes. Okay, I've got a triangle right here. Yes? Okay, can I go, actually I have two different triangles. Okay, I've got this triangle and that triangle. I've got a triangle right here. I've got a rectangle. I've got a small triangle. Okay, I've got another triangle right there. And I've got a rectangle there and a little triangle. Now, if the shape is below the x-axis, will the area be negative? Yes, it will. All right, so keep that in mind because we're looking for a vector quantity here. All right, I'm going to give you a couple minutes. Calculate the areas of all those shapes and tell me what the total displacement of this object is. Just eyeballing that, is it going to be positive or negative? Probably negative. It looks like it spends more time going backwards than it does going forwards. All right, okay, give you a couple minutes. Okay, so let's have a look at this here. I want to calculate the area first of this little triangle here. Okay, its base is 3, and its height is -3. So 3 times -3 is -9 divided by 2. Right, so this triangle here is -4.5. I've got this triangle here that's -3 tall by 1 on the base. So its area is -1.5. I've got this little triangle here, okay, whose base is 1 and its height is +2, right? So its area is +1. And then I've got this rectangle here that is 1, 2, 3, 4, 5 wide by 2 tall. So it's +10. Okay, I've got this little triangle here whose base is 1/2 and its height is 2. So 2 times 1/2 is 1 divided by 2 is 0.5. And then I've got this tall triangle here whose base is 1.5 and its height is -6. 6 times 1.5 is 9 over 2 is -4.5. All right, I've got this triangle here whose height is 4 and its width is 2. So 2 times 4 is 8 over 2 is 4. And I've got this triangle here, this rectangle here that's 1, 2, 3, 4 wide by -2 tall, so it's -8. And then I've got this one here that's -2 tall by 1 wide. All right, so that's going to have -1 for an area there. Okay, everybody follow me on that one? So now we just got to add all those together. Okay, with the signs so that we get the actual displacement of the object. So we'll have negative 4.5 plus negative 1.5 plus 1, okay, plus 10 plus 0.5 plus negative 4.5 plus 4 plus, whoop, sorry, that should be negative 4 plus negative 8 okay, plus negative 1. All right, negative 12. All right, so our total displacement there is negative 12. Is that cumbersome? Yes, it is. All right, which is why on an exam I would never give you one that required you to find the areas of that many shapes. Obviously, it would be quite a bit shorter, right? I would only ask you to show me you remembered, okay, or were able to figure out that that's what you were supposed to do. All right, if I know the total displacement, can I find the average velocity? Okay, do I need any special graphing tricks to find average velocity if I know total displacement and total time? No. I can just go straight to my formula sheet. Okay, and go, oh yeah, average velocity is total displacement, negative 12 meters, over total time, 20 seconds. Okay, everyone follow me there? Right, and the reason I'm saying 20 seconds is because that blue line does actually reach over. It's just stopped for the last second here. Okay, and so that would give us negative 0.6 meters per second. Right, and then find the average acceleration between 14 and 20 seconds. We're going to skip that one because we haven't gone over the formula for acceleration yet, that VF minus VI over T. We haven't done that yet, so we'll skip that one for now. Okay, what about average speed? What two things do I need for average speed? Total distance and total time. So can I find the total distance? Yeah, I've already done really all the work for it. I just need to add all those numbers together without the negatives, and then divide that by 20 seconds, and I'll have the average speed. Right? So really, again, yes, we got a graph there, but the only thing we're using the graph for is to get the numbers we need. Okay? The rest of the stuff is the stuff we've done before, using the formulas, okay, doing our calculations, things like that. All right. All right, let's have a look at number 3 here, guys. So for the first part here, for part A, they want us to calculate the displacement from 0 seconds to 4 seconds. And this is a position versus time graph. All right, so on a position versus time graph, can I find displacement by doing this? Final position minus initial position. Yes, I can. Okay, and that's the only way to do it from this type of graph. Okay, what I see people do, and it's the people who memorize things, they memorize that it's area underneath the line, but not for this kind of graph. Okay, and so they make that mistake. All right, so I've got my final position here being, from 0 to 4 seconds. My final position is negative 4. And my initial position is 0. All right, so my total displacement from 0 to 4 seconds is negative 4 meters. All right, everyone all right with that? No, it's pretty straightforward. Okay, for B, the total distance traveled. Okay, well, so we know from here to here the distance is 4, right? Because in this part right here it doesn't go anywhere. All right, and then from here it goes from negative 4 to positive 6, which is another 10 meters. All right, so the total distance traveled is 14 meters. I just add them all up because distance is scalar. All right, for part C, average speed over the whole trip. Well, I just calculated total distance to be 14. The total time is 6 seconds. All right, so we go 14 over 6, okay, because, again, average speed is total distance over total time, so 14 meters over 6 seconds will give us 2.3 meters per second. All right, and then average velocity over the whole trip. Well, what two things do I need for that? Total displacement and total time. All right, I haven't calculated total displacement yet, but that's no big deal. The formula is still the same. All right, I start out, my initial position is 0. My final position is positive 6, so my total displacement is positive 6. And that takes 6 seconds. Well, 6 over 6 is 1. Okay, so total displacement over total time. We get 1 meter per second, and that has to be positive because it is in a forward direction. All right, questions on that one? All right, keep going then. Okay, guys, let's have a look at this one here. So we gotta use the velocity versus time graph here now, okay, to calculate the total displacement over the whole trip. All right, so what I have to remember is that displacement is average velocity times time. All right, that's right off of my formula sheet. So in these parts here where the velocity doesn't change, okay, the average velocity is easy to calculate. All right, sorry, I marked that one in the wrong spot there. Okay, the average velocity is relatively easy to calculate because, well, it doesn't change, right? But in these parts here where the velocity does change, and we have a triangular shape, okay, we have to use the average velocity, which is why we use base times height over 2 to calculate their area instead of base times height. Everyone follow me there? Okay, so we're really just using v equals d over t here. Is it supposed to be on 15? Is that what everyone kind of assumed? Okay, we'll just go with that then. Is that what my answer says too? Okay. Well, that was nice and straight. Anyway, okay, so we've got a 5 second, a 5 seconds, everything. The time intervals for all of the shapes is 5 seconds. So all we have to do is find, okay, average velocity times time. So average velocity is 8, negative 8, times 5. So this one's negative 40. Okay, this one's going to be half of that because it's got the same base, okay, the same height, but it's a triangle. So it'll be negative 20. All right, this will be positive 20. Do I need to bother with this? Or could I eyeball this and know that my total displacement is going to be 0? Right? Because, I mean, it spent the same amount of time below as it did above. All right? I mean, we should probably look at it anyway. But right, common sense would say that, well, if it spent the same amount of time going backwards as it spent going forwards, right, it should be 0. All right. Average acceleration between 5 and 15 seconds. Well, if I want to find average acceleration, okay, that is the change in velocity over the change in time. That's the formula that's on your formula sheet we haven't used yet. Okay, but that also means that that's the slope of the line. All right, the change in velocity over the change in time. So the change in velocity is positive 16 because it goes from negative 8 to positive 8, and that happens over 10 seconds. So we got 1.6 meters per second, or meters per second squared. All right, and then average speed over the whole trip. How do I calculate average speed? Total distance over total time. All right, so 60 plus 60 is 120 meters divided by 20 seconds gives me 6 meters per second for an average speed over the whole trip. So again, nothing here is really mathematically difficult. What presents challenges for people is the interpretation of the graph. How do I get this from this graph? What do I have to do? Okay? Once you figure out what you have to do, that part's actually pretty easy. Okay? The math in this is not overly difficult. All right? Making sense to everybody? All right, I'm going to post tomorrow's quiz probably shortly after lunch today. Okay? Have a look at it. It's going to be on graphing. Right, so it'll probably have like maybe one velocity versus time graph and one position versus time graph, and ask you to do some things with those. All right, so that'll be posted later today.